Thank you very much. Thank you very much for the nice invitation. It's a pleasure to be here. So in this talk, I will discuss some geometric analogs of classical harmonic functions on Rn and their associated evolutions. As we all know, harmonic functions are ubiquitous in mathematics and its applications. They arise, for instance, in complex analysis, potential theory, electrostatics, heat conduction, and many other places. So a harmonic function solves the Laplace equation, Laplacian of u equals 0, where the Laplacian is the sum of the pure second partials. The well-known Dirichlet principle says that harmonic functions are critical points of the Dirichlet integral, which is the integral of 1/2 grad u squared. The associated evolutions to this equation are the parabolic one, the heat equation, that was studied extensively by Fourier, and the wave equation, the D'Alembert, d squared t minus Laplacian u equal to 0. The geometric analogs we will be discussing, and which also have applications in physics, are the harmonic maps, which are functions instead of real values, are functions into a manifold M. M is a Riemannian manifold, and they are defined on Rn. And these harmonic maps were first introduced in the early 1960s by Eels and Sampson, and they are also critical points of the Dirichlet energy. This results in an Euler-Lagrange equation, which is a nonlinear PDE because you need a Lagrange multiplier because of the nonlinear constraint that u of x now is manifold value. To give you an idea of what these equations look like, when the target is the usual sphere S2 in the round metric, then the nonlinear equation becomes Laplacian of u equals minus grad u squared times u. Now remember that u is vector values because it takes its values on the sphere. The point of introducing these harmonic maps was to use them as a tool to study the geometric and topological properties of the manifold M. For instance, they showed, using the associated heat flow, which is known as the harmonic map heat flow, that smooth functions from Rn into M can be deformed continuously under certain geometric assumptions on M into harmonic maps. This work by Eels and Sampson inspired Hamilton to introduce his Ricci flow, which eventually led to the proof of the Poincaré conjecture by Perelman. Uhlenbeck also studied harmonic maps and introduced the notion of bubbling of harmonic maps to study their singularities. It turns out that this bubbling phenomenon is universal, as I hope to be able to explain later on, and is analogous to something called the soliton resolution, which we will be considering later. Let me now turn to the wave analog of the harmonic map heat flow, which are the so-called wave maps. So this is the wave flow associated with harmonic maps. This is a very vast topic, and I will only concentrate on aspects which are close to my own interests. There are several ways to define wave maps. A formal one is to consider the Lagrangian L of u d dtu, where you do minus dtu squared plus grad u squared, and consider the formal critical points. And the corresponding Euler-Lagrange equations are the wave map equations. In the case when the target manifold is the sphere, and we start from R2, the equation becomes d squared t minus Laplacian of u, so this is the D'Alembertian, equals to dtu squared minus grad u squared times u. And this is the wave map associated with harmonic maps. And clearly from these formulas, you can see that static solutions are harmonic maps, because this is 0, this is 0, and then that's the wave map, the harmonic map equation that I wrote earlier. So this wave map equation is Hamiltonian and time reversible, and it has a conserved energy. And the conserved energy is the one you can imagine, dt ut squared plus grad ut squared, 1/2, is an invariant of the motion. The wave map equations also are invariant under scaling. So if u is a wave map and lambda is a positive number, u of lambda t lambda x is also a wave map solution to the wave map equations, and the conserved energy is invariant under the scaling. And this is an energy critical equation because of that. It is the wave analog of the harmonic map heat flow, which is the parabolic analog of the heat equation. So as mentioned earlier, this inspired the Ricci flow, the harmonic map heat flow. And in the wave world, the analog of the Ricci flow is the system of Einstein vacuum field equations in general relativity. And so in a way, wave maps have a similar connection to the Einstein equations as the harmonic map heat flow has to the Ricci flow. So wave maps are natural geometric wave equations. They also arise as physical models in particle physics in gauge theories, what are known as nonlinear sigma models. As I said before, they are invariant under scaling, rotation, and translations of space-time, but they're also invariant under the group of Lorentz transformations acting on Lorentzian space-time. The theory of the Cauchy problem, which is the initial value problem for small data in the energy space for wave maps, was developed in works by Tataro and by Tao around 2000, while a theory for large data and short time was developed by Stervens and Tataro around 2010. When the target manifold M is a surface of revolution and we start from R2, there are special classes of wave maps which respect symmetries. So for example, when M equals S2, we can consider wave maps U such that when you compose them with a rotation, that's the same as rotating the target value k times. And we call this the k equivariant wave maps. So here k is a natural number, rho is a rotation of R2, and also a rotation of S2 provided we fix the axis, like the North Pole to the South Pole, let's say. The wave map for equivariant wave maps then admits a simplified version, which in polar coordinates r omega for this plane and eta theta for the sphere, fixing the axis, give you that tr omega by u goes to t eta theta, where t stays being t, eta goes to a function of r and t, and omega simply is multiplied by k. Now you can then derive the corresponding wave equation for psi, and this is the following nonlinear wave equation. Second derivative in t of psi minus second derivative of psi in r minus first derivative over r of psi plus the nonlinear term where the k, which is the degree of times you go around, plus sine of 2 psi divided by 2r squared equals 0. So this is the corotational, the k equivariant version of the wave map equation. The case when k equals 1 is sometimes called the covariant wave maps. This k equivariant wave maps have also a conserved energy, and it's given in this formula, dt psi squared r dr, just the natural measure in the plane, plus dr psi squared r dr, and then we get the k squared over 2 sine squared of psi r squared r dr. For general maps, from R2 into the sphere, the static solutions are just the harmonic maps from R2 into the sphere. There's a complete list of harmonic maps from R2 into the sphere. These were completely described in work of Eels and Wood in 1976. The traveling wave solutions for wave maps are also known, and they're simply the Lorentz transforms of the static solutions, of the harmonic maps. And these are what take the role of bubbles in harmonic maps for wave maps. The K-equivariant bubbles are all static because the Lorentz transforms destroy the K-equivariant symmetry. And so they're just time independent. And they correspond to the static solutions of this K-equivariant equation. And these are, of course, explicitly known, and they're given by the following formula. Q sub k of r is twice arctangent of r to the k plus L pi, where L is an integer. The one of least energy among all these static solutions, which is actually the harmonic map of heat of least energy among all non-constant harmonic maps, not just the equivariant ones, is Q sub 1, which is 2 arctangent of r plus L pi. The L pi doesn't do anything to the energy. And it is called the ground state because it minimizes the energy. So since this happens to be K equivariant with K equals 1, that means it's co-rotational, it puts particular emphasis on the co-rotational case. The well-posedness in the theory in the energy space for the K equivariant case is much simpler than for general wave maps, and was done substantially earlier, goes back to work of Chatin and Tavildar-Zadeh in 1994. The issue of singularity formation for wave maps was open for many years. In the equivariant case, blow up can only occur at the origin and in an energy concentration scenario, which is this bubbling. This was shown in a pioneering work of Struve in 2003. So who showed that singularities can form only by bubbling off of non-constant harmonic maps. Constructions of actual solutions which blow up came a bit later. They were built by Krieger, Schlag, and Tataru in 2008 in the co-rotational case K equal to 1, by Rodniansky and Stervens around 2010. Actually, they were obtained simultaneously, just that the paper appeared much later. And then Raphael and Rodniansky constructed a new family of blow-up solutions, which gave rise to stable blow-up in 2012. Now, there was a threshold conjecture for general wave maps, which was established by Stervens and Tataru in 2010, which which proved that if the energy of the wave map is smaller, strictly smaller than the one of the ground state Q, which is a number that we know, I think it's 4 pi, the wave map has to exist for all time, so there is no blow up, and it scatters. It means that at infinity, it behaves as a linear solution. So the issue then becomes, what happens for the long time behavior of wave maps when the energy is above the energy of the ground state? And this is the issue I'm interested in. And you can ask this general question. So what can one say for general wave maps of energy above Q? For K equivariant wave maps, or for co-rotational wave maps in a decreasing level of generality. So an approach to how to answer these questions is suggested by the soliton resolution conjecture. The soliton resolution conjecture predicts that any global in time solution of a nonlinear dispersive equation evolves asymptotically as time goes to infinity as a sum of decoupled solitons. And these are called, these sums are called coherent structures, plus a radiative term, which is typically a solution to a linear equation. Solitons are nothing more than traveling wave solutions, so solutions that, as time evolves, just get translated in time, which are well localized, and they travel at constant speed. And the speed can possibly be zero, and then we would have the static solutions. We expect this type of decomposition as time goes to infinity, but also for finite time blow-up solutions, depending on the nature of the blow-up. So this soliton resolution conjecture has a very interesting history. It arose in the 1970s from numerical simulations and from the theory of integrable differential equations. So this all goes back to a numerical simulation carried out at Los Alamos in the early 1950s by Fermi, Pasta, and Ulam, which was the birth of a scientific computation, the first time that a computer was used to simulate the solutions of a nonlinear partial differential equation. And in carrying out this experiment, they used the same computer that had been previously used for the calculations of the Manhattan Project that led to the atomic bomb. And after the war, Fermi wanted to do something scientific with this tool. And so he proposed he proposed scientific computation. He actually called this a minor discovery. And he found a puzzling paradox was found. I don't go into details into what this paradox is, but about 10 years later, 15 years later, Martin Kruskal found an explanation for the Fermi-Pasta-Ulam paradox. Fermi died without knowing the explanation. And he was able to find an explanation through the existence of solitons for the correct de Vries equation, which is this one-dimensional equation that governs the motion of water waves in shallow channels. After this discovery of Kruskal, Zabusky and Kruskal conducted another very influential numerical simulation, which showed the emergence of solitons and multisolitons, which are these coherent structures, superpositions of solitons, for the KdV equation. This numerical simulation led directly to the formulation of the soliton resolution conjecture that I just mentioned, but also to the theory of integrable nonlinear equations, because in one of the experiments, they saw that if you start with two different solitons, the evolution of a correct de Vries equation, and they travel at different speed, once they collide, the collision is elastic in the sense that they emerged after a while unscathed. They preserve their shape as if they were solutions to a linear equation, which of course they're not. So integrable nonlinear equations can be solved by a reduction to a collection of linear problems. This is work pioneered by Lax. It's a very important class of equations in nonlinear science, but it has the disadvantage of being non-generic. Soliton resolution has been proven for a few integrable cases, like the KdV. The proofs are, even in the integrable case, extremely challenging, and there are issues that are still unresolved. There have also been results in perturbative regimes near solitons, even for non-integrable cases. This phenomenon of soliton resolution, again, seems to be universal. It has been observed numerically and experimentally, for instance, in the dynamics of gas bubbles in a compressible fluid, and this you can see in a lab, and in the formation of black holes in gravitational collapse. Of course, we don't see that in a lab. We see this numerically. And this mechanism for relaxation to a coherent structure, which has been observed numerically and experimentally, seems to be the radiation of excess energy to spatial infinity. So the energy, of course, is conserved, but is pushed out to spatial infinity. So proving soliton resolution in non-integrable settings is a major goal for nonlinear dispersive and wave equations. For example, a very far-reaching conjecture in general relativity is called the final state conjecture. It states that the evolution of general sets of initial values for the Einstein vacuum field equations, which are the analog of the Ricci flow, as I said earlier, leads to the superposition of a finite number of Kerr black holes for very, very large times, which are the solitons, plus a decaying, locally decaying radiative term. Now, this conjecture is considered completely out of reach. We probably will not, none of us will see a proof of this conjecture, but it motivates the corresponding problem for Wavemaps. So in the last 12 years or so, in collaboration with Ducaer and Merrill, also with Gia, Martel, Cott, Laurie, Schlog, and more recently with Collot, we have been studying this type of issues for Wavemaps and also for the closely connected energy critical nonlinear wave equation. This is the following semi-linear wave equation. We have the D'Alembert of u equal to the power u to the 4 over n minus 2u times u itself. So, and you give the initial data u0, which has a gradient in L2, and the time derivative u1, which is a function in L2. This equation also has a conserved energy, but this does not have a sign. So that's an interesting feature of this equation. And there's solutions with negative energy. In this setting, with Ducaer and Merrill, we introduced a method which we call the energy channel method, which gives a mathematical way to measure this radiation of excess energy to spatial infinity. Let me first explain a little bit the connection between radial nonlinear wave equation and the corotational wave map equations, to show you why the two theories are connected. Because now we're going to look at the radial nonlinear wave equation in 4 dimensions. In this case, the nonlinearity becomes merely u cubed. In dimension 3, let me just say for further clarification, is u to the 5. So suppose we take a solution to the corotational wave map equation, and we consider u of tr to be square root of 2/3, that's 2/3, c of tr over r. What equation does u verify? Well, you calculate, and we get the linear part, which, if you notice, is the radial D'Alembert in 4 dimensions. And it equals 1 over r cubed, capital lambda of r times u, where capital lambda of u is given by this formula, u minus square root of 6u over square root of 6. And this lambda is odd, like u cubed, is smooth like u cubed, and for u small, it has behaves very, very closely to u cubed. I mean, you just do a Taylor expansion to see that. Okay, so that's why the two theories are connected. So let me now turn for a little while to the nonlinear wave equation in R cross Rn. The radial stationary solutions are given by this explicit formula. These functions are well known in geometry because they arise in the study of the Yamabe problem in differential geometry. So the first breakthrough result on soliton resolution for the nonlinear wave equation was in the radial case, n equals to 3, where with Ducaer and Merrill, we proved this decomposition, where the solitons are the static rescalings of this function w I wrote before, when n equals 3. And the decomposition was proven for all radial solutions for infinite time, and for finite time for solutions which remain bounded in the energy. The key point of the proof was that if U is a radial solution of the nonlinear wave equation when n equals 3, and U is not one of the static solutions, which are listed here, 0 or plus or minus W lambda, then there is an energy channel. For all positive T or for all negative T, you can find a fixed amount of energy outside a translated light cone for all times. So this is the channel of energy that persists for all times. And it persists either for all positive T or for all negative T, unless you are one of the special static solutions, which do not have such an energy channel. This inequality, which I call 1, captures the observed radiation of energy to spatial infinity. So the proof of 1 relies on something we call the outer energy lower bound for radial solutions of the linear wave equation. So this is a very elementary result in its proof. It says that for all T positive or all T negative, for whatever R naught bigger than or equal to 0 you choose, you can bound the gradient of V squared dx uniformly for all T positive or for all T negative by basically the energy of the initial data. Now, we have to correct the energy of the initial data by making an orthogonal projection to the orthogonal complement of the one-dimensional subspace spanned by the Newtonian potential, 1 over R. And 1 over R is a counterexample to this quantity being positive. So, but it's the only counterexample. So if you do the orthogonal projection to its complement, then you get the lower bound. The proof of this could have been done by D'Alembert. So that's all I want to say. It's a one-page proof. To use this channel of energy in the nonlinear case, a key point is that the ground state asymptotically behaves like the Newtonian potential for R large. So it matches the counterexample, and it's excluded then in the bound for the nonlinear solutions. So let me now speak a little bit about inequalities. This inequality 2 has an analog in the non-radial case, but only when R naught is 0. And it's valid for all odd dimensions n. And it says that for all T bigger than or equal to 0, or for all T less than or equal to 0, the gradient on the outside of the light cone is controlled by the initial energy. So there's always half of the energy is outside of the light cone. And this was proved with Ducaire and Merle in 2012. Now, it's an interesting fact that these two outer energy inequalities for the linear wave equation fail for all even dimensions. It's not that we couldn't prove them. Well, we couldn't prove them, but it's not just that we didn't know how to prove them. They fail. And this was done in a paper with Kott and Schlag in 2014. Now, the curious thing is that in dimensions 4, 8, 12, 16, and so on, it holds for data of the form V0, 0. And for the other ones, 6, 10, 14, it holds for the other set of data. And these proofs were done by using Fourier analysis. So the inequality 2 that I have here fails completely in the non-radial case in all dimensions. And there's an infinite dimensional set of examples, one for each spherical harmonic. Now, this inequality 2 that I just showed, I'll flash it again, has an analog in the radial case for odd dimensions, but there's a larger exceptional space. So there's a space piece of R naught, a finite but a higher dimensional exceptional subspace, which has dimension n-1/2. So the dimension goes to infinity as the dimension of the underlying space goes to infinity. So because of this, the validity of this exterior energy channel and of the decomposition of the soliton resolution was in question for all other cases other than dimension 3 radial for a very long time. Nevertheless, we tried to obtain weaker results, and weaker results were obtained through using an idea that originates in the study of the parabolic harmonic map heat flow, which is to use time averaging of the flow and try to find monotonicity formulas for that. And using this idea, we were able to prove the full soliton resolution for the nonlinear wave equation in the radial case in all dimensions, but not for all sequences of times, but for well-chosen sequences of time that depended on the solution. And this had to assume the boundedness of the energy norm until the final time of existence. This is a natural assumption in this setting. And this was done in the case of odd dimensions by my former student, Casey Rodriguez. The first even dimensional case we did with Koch, Laurie, and Schlag in 2014, and all even dimensions we treated in the paper with Hao Jia in 2017. We were also able to treat the non-radial case, and then the solitons are the Lorentz transformations of the solutions of the nonlinear elliptic equation. And we did this, let's say, in the small dimensions. The dimensionality restriction is a technical point. It's not a crucial point. And this was in a paper with Lucaire, Gia, and Merle, again, for bounded in the energy norm solutions by monotonicity of time averages and valid for well-chosen sequences. Now, the method of proof that uses monotonicity after time averaging cannot give the decomposition for all times. And this is an interesting fact already known for the harmonic map heat flow. Topping in 1997 found that if you change the manifold not to be the sphere, but another smooth manifold that he constructed, the decomposition cannot hold for all sequences of times. It is dependent on the sequence of times. However, it is conjecture that if the target is the sphere, this does not happen. And this is still an open problem today. So let me turn to recent works. In a sequence of 3 papers that we posted on arXiv at the end of 2019, we were able to prove the full decomposition for radial nonlinear wave equations in all odd dimensions for solutions that remain bounded in the energy space. And the idea here was to study the collisions of solitons. You may remember that I mentioned that in the Zabusky and Kruskal paper on numerical simulations for KdV, the numerical simulations showed that for KdV, the collisions of solitons were elastic, that the solitons just crossed over each other and came out unscathed. And it turned out that this was proven to be a consequence of the fact that the KdV equation is an integrable equation. And this was one of the first great triumphs of the theory of integrability. Now, what we're showing here is that in non-integrable cases, all of these equations are non-integrable. This elastic collision of solitons always fails. And what happens is that some radiation always is left over. And this is what's, this radiation left over is this excess energy that goes to spatial infinity. Okay, so in the rest of the talk, let me return to wave maps into the sphere. And in this case, the boundedness of the energy norm is automatic because the energy for wave maps is positive. So if you are in the energy space, since the energy is conserved, the energy will be bounded for all times. So these extra assumptions that we had to impose in the nonlinear wave equation are automatic for wave maps. So the first works in the direction of soliton resolution for wave maps were by myself with Kott, Laurie, and Schlag in 2015. And we established the decomposition for co-rotational one equivariant wave maps into S2 under an energy constraint on the wave map, which implied that in the decomposition, only one bubble would appear, only one solitary wave would appear. And shortly after, Kott extended this to general data, but again, for well-chosen sequences of times, because this also involved monotonicity after time averages. You can think of the time averaging trick as the same as what when studying series one does, and one pass from maybe summability of the series doesn't work, but Cesaro summability does. And that's what this time averaging does. Okay, with GIA, we extended Kott's result to all equivariant classes for, again, for well-chosen sequences of times. And Engelstein and Mendelssohn in 2020 showed that the topping example also is found for the wave map setting. So if the target is not the sphere, you could have that different sequences of times yield different compositions. So in the K equivariant case, Genders and Laurie in 2020 established the decomposition for all times, provided at most two bubbles appear. So in the first works, we had at most one bubble. They were able to show that this decomposition when at most two bubbles appear. And this was a great advance. Let me now turn for a little while to general wave maps into the sphere without any symmetry assumptions. And here very little is known. There was a very nice thesis written by Greeny in 2016 at Oxford, where he obtained a decomposition for general wave maps for well-chosen sequences of times, but the error term doesn't go to zero in energy. It goes to zero in very, very weak norms. With Dwicker, Gia, and Merle in 2018, we took up this issue and studied the case when the data is just an epsilon bigger than the energy of the ground state. So the case where it's not covered by disturbance Totaro threshold conjecture proof. And we established this decomposition, at least in the finite blow-up case. So let me now turn to the very recent result, which establishes the full decomposition for co-rotational wave maps into the sphere. So this is the first unconditional soliton resolution for wave type equation in an energy critical setting. So the energy space will be just a space of functions for which the energy is finite. If you recall the definition of the energy, this is the energy. And we call E the space of data for which the energy is finite. And I recall that the co-rotational wave map is this nonlinear wave equation. The nonlinearity is sine 2c over 2r squared. And the energy is preserved for solutions of this equation. Now, let me go back and notice this term here. We have sine squared psi naught over r squared, and it's r dr. So the R, the R, and the R squared give me a dr over R. So some cancellation has to take place so that this integral is finite at 0 and it's finite at infinity. And it's easy to see that to be in the energy space, then you have to have limits at the spatial 0 and spatial infinity, and they have to be L times pi and M times pi for some integers. Okay. Now this induces a fibration of the energy space into these fibers, and we call them HLN. It's an affine space, and the underlying Hilbert space here is the one where 1 over R squared R dr psi naught R squared is finite. Okay, and we call this H, which coincides with H00 in this terminology. And the ground state is twice R tangent of R, and it is in the space H01. Yes, value 1 at infinity. Okay. So all the stationary solutions are, this is the list. L pi plus or minus q of lambda R, where lambda varies on the positive fields. So the first theorem gives the soliton resolution, was proven in early 2021. So if C is a corotational wave map in the energy space with maximal time of existence t plus, then one of the following holds. Suppose that t plus is finite, so that the thing blows up in finite time. Then there's a fixed element of the energy space, the radiation term. There are signs I sub j that give me the form of the static solution, and scaling parameters, lambda j, that define near the final time, such that these scales are well separated. The ratios of consecutive ones tend to infinity as time goes to the final time. So these waves are well separated. These stationary solutions are well separated from each other. And we get the resolution. Our flow at the blow up time equals the radiation term plus the sum of the rescaled stationary solutions. And if the time is infinite, there's a complete analog, and there's a complete analogy with this result. Now, instead of a constant phi naught phi 1, we have a linear solution of the associated linear wave equation for the wave for the Hilbert space that we're considering, and that's why we have the potential 1 over R squared here. And the initial data is in the energy space, and there's signs that give you I forgot to write them in here. They have to be ij there, which tell you what are the stationary solutions we use, and these are scaling parameters, which are always less than the speed of light, which is t, and our solution then is written as the linear solution, the radiation term, plus the sum of the solitary waves. So this is the full decomposition. There's some compatibility conditions that let's omit. And the key point is in the proof is the following rigidity theorem, which is the analog of the channel of energy for the radial 3D nonlinear wave equation. So suppose I have a function in the energy space, and suppose that it's not the data of a stationary solution. And that's what this description tells you. Then there is an eta positive such that for all t positive or all t negative, there's always some energy outside of the light cone. There's always a channel of energy. Okay? And this gave the soliton resolution for corotational wave maps. But things move quickly in this area at this point because we've had all these breakthroughs and now we have this accumulation of information. And more recently, in mid-2021, Genters and Laurie extended the theorem 1 about the decomposition to the K equivariant case for all K. But they did not prove this this channel of energy. They used a different method based on the idea of no return lemmas in dynamical systems, which was introduced to the study of wave equations by Nakanishi and Schleib. But time moves very fast now. And in work, I say being written up now, but the first installment appeared on archives last week. And with Collot, Vicaire, and Merle, we have obtained the corresponding decomposition for nonlinear wave equation. Oh, maybe I forgot to say, let me go back. Yeah, that when we did the co-rotational wave maps, we also did nonlinear wave for n equals 4. And you saw how those two equations were very related. So now we were able to do the 6-dimensional case, introducing a whole bunch of new techniques. We now were able to find that there is a weak form of the channels of energy, exterior energy estimates, that don't hold for the linear wave equation, but they hold for wave equation linearized around the ground state. And we were able to show this outer energy inequality for all the equivariant cases too. And I think this now will settle all the symmetry cases in which symmetry is present for the nonlinear wave equation and the K equivariant wave maps and the related Young-Mills in radial and equivariant cases. But this will be appearing in a series of works to appear. So with that, I conclude. Thank you very much.
Okay, thank you very much, Carlos, for the very, very interesting talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Okay, if not, thank you very much, Carlos, for the very, very interesting talk. Thank you very much.
Thank you. Thank you for the invitation. Thank you for
Thank you very much.
For
Thank you very much. Thank you very much, everyone, for coming. Thank you.
Yes, thank you all.